Okay, let's dive right in. So there's this puzzle, right? Been around for over a century, sitting right there in physics. It's basically asking, can math, precise logical math, actually describe the physical world, which often looks kind of messy. Feels like a huge question, maybe overwhelming. But today we're looking at some really interesting research, might have an answer. And you really don't need a PhD in physics to get why it's a big deal.
Yeah. And it goes way back, 1900. This massively influential mathematician, David Hilbert, he set out 23 huge problems, kind of like the ultimate math checklist for the new century. And number 6, that was the one. Can we build a truly rock-solid mathematical foundation for, well, for all of physics?
Exactly. He wasn't just, wondering casually. He was asking if there's a fundamental code, a mathematical structure under everything.
Yeah.
Now, boom, over 100 years later, researchers Yu Deng, Zahar Hani, and Xiao Bao, they put forward a framework, and it might just be the key.
Well, if you step back a bit, what they might have done is huge. It's about linking 2 pillars of physics. You've got classical mechanics, how individual things move, like billiard balls, and then thermodynamics, heat, energy, how lots of particles behave together. And the kicker is they're suggesting a single mathematical way to connect them.
Right. So for you, our listener, you shared a news piece from Earth.com, hints at real-world stuff.
Yeah.
And also an excerpt from their technical paper on rkv.org. Definitely dense. Our job today, connect these dots, why the buzz, and let's try not to drown in the equations, yeah.
Okay, so Hilbert's 6th problem, what was he really after? It wasn't just about, hey, let's use some math and physics. We were doing that already quite well, actually. No, it was deeper. Can we find, like, fundamental mathematical rules from which the laws of physics just naturally emerge, especially when you look at different scales?
Yeah, so it's more the description. It's about derivation, right?
Yeah.
Showing how the equations we use come from something more basic.
Right.
And specifically, that 6th problem, it zoned in on the links between different levels. Like, how do all those jiggling atoms and molecules somehow create smooth-flowing water or air?
Precisely. And that's exactly where this new research slots in. Deng, Hanini, and Ma, they've potentially built that mathematical bridge. They're connecting 3 levels. First, the actual collisions between individual particles, tiny scale. Then the kinetic view, that's more like a statistical description of lots of particles moving around. And finally, up to the fluid models we use every day for air, water flow, the big picture stuff.
Wow, okay. So from tiny bangs up to swirling winds,
Yeah.
all under one mathematical roof. That sounds ambitious.
It is. And the technical work behind it, that's what's really turning heads. Our 6th paper talks about achieving a rigorous derivation of Boltzmann's kinetic equation from the hard sphere system for rarefied gas. Okay, that's a mouthful. Let's maybe break that down a bit.
Yeah, please do. Boltzmann's kinetic equation. Sounds important. What is it in simple terms?
Okay, think of a gas like air, loads of tiny particles whizzing around, bumping into each other. Boltzmann's equation. It's basically math that describes how the distribution of speeds and directions of those particles changes over time. It tracks the overall picture, the statistics, not every single particle path. It factors in all those collisions.
Got it. So not following one molecule, but seeing the whole crowd's behavior, the trends.
Exactly. Now, the big challenge for decades, really, was proving you could get this statistical equation directly from the basic rules of particle collisions, like starting with just simple hard spheres bouncing off each other. There was this guy, Lanford, back in '75. He made progress, showed it worked, but only for a really, really short amount of time, like just after the collisions start.
Ah, okay. So Lanford opened the door crack, showed a glimpse, but couldn't prove it held up long term.
You got it. And that's the breakthrough here. Deng, Honey, and Ma, they've apparently extended this derivation to work for, well, arbitrarily long time. As long as the Boltzmann equation itself still holds, their derivation works, and they say it right in paper. This is a crucial step towards resolving Hilbert's 6th problem. It potentially connects the microscopic mechanics of the statistical picture over meaningful times.
Yeah, okay, now this is where my brain starts buzzing. The paper mentions molecular chaos. Sounds messy. What's that about? And why has justifying that been so hard when trying to get to Boltzmann's equation?
Right, molecular chaos, or the fancier name is Stossel-Ansatz. It's a key assumption. It basically assumes that before 2 particles collide, their velocities are totally unrelated, statistically independent, like strangers meeting for the first time. It simplifies the math enormously, lets the Boltzmann equation work, but proving it rigorously, that's the tough bit. Because realistically, after particles collide, their futures are linked, right? There are correlations. Think of a crowded room again. People bump into each other. Afterwards, where they go next isn't totally random. It's affected by who they just hit. Molecular chaos sort of ignores that lingering history.
So the assumption makes the math work, but it feels a bit like cheating reality, because particles do have histories that affect future collisions.
Well, yeah, that's been the mathematical headache. Justifying that assumption, showing it holds true enough on average, especially over long times, that's been the hurdle. And these researchers, it seems, have found a way to rigorously handle that within their framework. That's a big part of the achievement.
Wow, okay. That does sound major. The paper also mentions their next step, something about a second hydrodynamic limit. What's that, and how does it get them closer to, like, fully solving Hilbert's problem?
Okay, so they've connected particle collisions to the statistical Boltzmann equation. That's step one, roughly. The second hydrodynamic limit is about the next step, taking that statistical picture from Boltzmann and rigorously deriving the equations we use for large-scale fluid flow, like the Navier-Stokes equations for water or air. Basically, it's completing the bridge, going all the way from individual particle mechanics through the statistical kinetic theory right up to the continuous fluid dynamics we see. They believe nailing this final link will provide that full resolution to Hilbert's sixth problem, a complete mathematical path from micro to macro.
Okay, I think I see the whole journey now. Particles, statistics, fluids, all connected by rigorous math. That's quite something. So let's shift gears a bit. Let's talk practical stuff. The Earth.com article you shared hinted at real-world impacts. What could this actually mean down the line?
Well, the big one mentioned is better modeling, specifically air and ocean flow. Think about things like hurricanes or really turbulent currents in the ocean. These are incredibly complex. The physics behaves differently at small scales versus large scales within the same system. Modeling that accurately is really hard.
Yeah, predicting a hurricane's path.
Yeah.
Or its strength. It's always so much uncertainty. It feels like we're still guessing sometimes.
Exactly. So if you have a unified mathematical framework that properly connects those scales, it could potentially lead to much better models. The article specifically calls out weather forecasting. Imagine more reliable warnings for severe weather. That's a huge potential benefit.
Definitely. That alone would be massive. Anything else? Beyond weather.
Yeah. They also touch on designing more efficient engines. It sounds like a leap, but if you understand the fluid dynamics, the gas flow, the fuel mix at a more fundamental level across different scales, engineers might be able to optimize things much better, maybe get more power, use less fuel, reduce emissions. It's about really grasping the underlying physics.
So from saving lives with better storm warnings to, I don't know, more miles per gallon. That's quite the range from some pretty abstract math.
It really is. It highlights how this kind of fundamental, curiosity-driven research, even purely mathematical questions posed over a century ago, can eventually ripple out and have really tangible effects.
So wrapping this up a bit, for you, the listener, what are the really key things to take away from this deep dive? We went from Hilbert in 1900 to potential breakthroughs today.
I think the core idea, the really aha moment, is that mathematical connection. How the seemingly random, chaotic motion of billions of tiny particles can be rigorously shown to lead to the smooth, predictable flow of fluids we see around us. It's about the power of math to find order and structure hidden within apparent chaos.
Yeah, it really drives home that math isn't just calculation. It's a language for describing reality, for understanding the deep connections, and that even super abstract work can eventually touch our everyday lives in unexpected ways.
Absolutely. And maybe the thought to leave you with is this. How many other areas of science seem totally separate right now, but might actually be linked by some underlying mathematical structure we just haven't found yet? You know, what other big unifications might be out there waiting to be discovered?
It's a great question to ponder. If this has piqued your interest and you want to follow the story, you could definitely search for Hilbert's sixth problem. Or look up the researchers, Yu Dang, Zahir Hani, and Xiao Ma. See where their work goes next.
Yeah, and thanks for sharing those sources with us. It's been fascinating to dive into this really